I could make a very big introduction for her because she has done a really impressive list of things, but she told me to be short because she wants to make the most of the time and talk about the stuff she's going to talk. So very briefly, she was an ESO fellowship in Garching when she started doing research. Then she became a staff astronomer in the Instituto di Radioastronomia in Bologna. And at present, she's the senior astronomer at ASTRON in the Netherlands, and she's also full professor at the Captain Astronomical Institute of the University of Groningen, also in the Netherlands. And I would like to emphasize that she has been the PI of one advanced ERC advanced grant, Radio Live. And actually, some of the results that she's going to present today are related to this advanced grant. So I'll let you speak, Raffaella. Thank you.
Thank you. So, thank you for, of course, for the invitation. That was great. It was great to be here. Thank you for being here and listen to some of my the result that I would like to show you. So I'm going to talk about jets, the radio jets that I know is not really the hot topic in this institute, but I'm going to put them in the context of galaxy evolution or outflow and this kind of thing. So I hope you will find some of these results interesting. So of course I'm standing here on behalf of a number of people that did a lot of work, most of the work that I'm going to show. So. Some, you know, old-time kind of collaborators, Clive, Tom, but also some enthusiastic young people, students, and like Sua and postdoc, and some of them also connected to the ERC, by now finished, unfortunately, but okay. So I'm going to tell you about the radio jet and the impact they may have. I'm not going to, in the context of feedback, AGN feedback. Unfortunately, I don't have a final sure result. Of course, it's a complex topic, but the aim is really to give to also the people that develop a model of galaxy evolution, some constraint that they can use to include in that simulation. So, so let me start with some introduction. The idea is to look at AGN feedback that is something that we consider very important. So the impact that the energy released by the active black hole can have on the host galaxy. And this is considered to be important for either for preventing star formation or for regulating the growth of the black hole. Fine. So I'm talking about massive galaxies, so I will forget about star formation as a driven mechanism. So I'm really going to focus on AGN activity. So, so typically when people talk about this, they talk about two types of feedback, a bit of black and white kind of pictures. So the jet, typically they appear in this so-called jet mode, surprise, surprise, or maintenance mode. So this is more on the large scale, intergalactic scale, so where the jet, the role of the jet is to prevent the cooling from the hot gas. Okay, but this is in cluster, so they are big jets, so it's a certain situation that you may have. Very often, instead, is the quasar mode, the one that is considered, so with outflow of gas, so clearing the galaxy from gas. These are very common, but typically they are considered driven by radiation or wind. And so what I'm going to argue in this talk is that also radio jet can play a role in this feedback mode. And actually, this is an example of a simulation, illustrative simulation, one where the feedback from AGN is included. You see every now and then this burst of explosion in a way in all directions. that already doesn't look like what we are really observing. But anyway, this is the way feedback and wind are implemented. But already this kind of simulation, although the most up-to-date, they have some problem with the gas fraction that they predict, with the stellar mass, when they are outside cluster. So it's not all solved. It's not that AGN feedback is done and that's it. We are by far with plenty of open questions. And so, and also while studying the AGN feedback, we have really encountered a variety of mechanisms. Actually, for somebody that really likes AGN, like me, so I don't really worry about the feedback so much. It's cool because they give you a grant if you have that as a topic. But AGN are interesting objects in themselves. We have really learned a lot about this. Also surprising thing, as I'm going to show you. So for AGN feedback, there are, first of all, as I say, a variety of mechanisms. So wind start already from the accretion disk, observing X-ray, radiation, we know all about that, more or less jets. But what we have also learned is that the outflow that they produce are multi-phase, meaning that there are all the phases of gas involved in them. And we knew about the ionized gas, the hot gas, but the surprise was that also the cold gas is involved. So in this outflow, you find molecular gas, you find H1, and also the mass outflow rate that they carry seems to be the largest one. So essentially, if you want to know the impact of this outflow produced by the AGN, you need to know about gas in different phases and really associate the energetic to this. So that makes even more complicated. And then at the end, I will also look into more the turbulence, not only the outflow. So in all this complicated scenario, I'm going to add also the jets. And I think they have some relevance. So what I want to show you is are a few examples of work that we have done. So I want to show you one object at the beginning that kind of summarizes the work that you can do in to characterize outflow driven by jet. Some about the statistic, because at the end you want to know how common they are, whether really you should worry or not. And a few examples also connected to the study of the H1 and the molecular gas as a function of the radio power, because you will see throughout the talk that of course there are different types of jets, different power, so we have to see what they can do. And most of the work that I present you is done using either H1 observation or molecular gas observation CO from ALMA. Okay, so before I really start with my work, let me say, just spend 2 slides on key points. I think they are relevant for also to convince you that there is a reason to look at the jets. First of all, you may wonder, but they always told me that jets are rare. Only 10% of the galaxy have jets, so why should I worry about them? And so I would like to emphasize that actually the presence of radio AGN is very much function of the stellar mass of your galaxy, of the host galaxy. So if you look here, these are some recent results from work connected to LOFAR, by the way, from Sabater and Best, where you see that depending on the stellar mass of the galaxy, the fraction of radio AGN can be very high. So if you have the most massive galaxy here, they go well above the usual 10% that is mentioned. The other thing is that it depends also on the radio power. So on this axis, you have the radio power of your galaxy at 2 different frequencies, doesn't matter so much. And this is a sort of first order division between the what's so-called radio loud and radio quiet. So typically when people talk about radio quiet means they just want to ignore the radio, and that's it. That is a solution. I mean, I'm not saying, But actually radio quiet doesn't mean at all that they are radio silent, and as you see, they are the most common. So if we can check whether this object actually also play a role in all the business of driving outflow, that's very important because the fraction then of your radio interesting object increases. So this will appear a few times in the talk. And then I want to mention the new result or development in the numerical simulation. So the jet used to be a very collimated thing, laser-like, that would enter your galaxy, uniform, distribute an ISM, and that's it. While the most recent simulation have a jet that start and they enter a clumpy medium. So here you see two simulations. The first one is with higher power jet. So if you launch this jet in a clumpy medium, what you see, and we are talking about the kiloparsec scale here, what you see is that the jet hits all these clouds that are there and create a sort of cocoon of shock gas around it. So the impact of the jet becomes not so much the head of the jet pushing something, but the entire cocoon of gas affected by this interaction. And even more evident is for a low power jet, the famous or infamous radio quiet, in which the jet really struggle to get out, and so create even more this cocoon, this disturbed cocoon around. And it stays also trapped in this medium for much longer. So all the energy gets dumped there. So the idea from this simulation is, first of all, that you have some lateral effect to the jet, not just the head of the jet doing this, and also that the effect may change and may be relevant also in low power object. So this is a kind of summary of this. So you have a different region of the jet and the environment that are affected. Okay, so this type of simulation have guided the interpretation of our observation. So let me show you the first object that kind of summarize. It took ages to. So I'm summarizing in 3 slides the work of, I don't know, 10 years or maybe more. But so this is a Seyfert-2 galaxy. So you will say that has a lot of radiation. That's the one that drives all the outflow that you see there. And it's a low power Seyfert-2 galaxy. 1068 like for the one that like 1068, but is actually a different one, but doesn't matter. So, so this is a summary of what we knew about this galaxy. So it's actually is a radio source. This is a radio source in contour. This is a core, and these are the 2 jets or lobes. It's about 1 kiloparsec in size, and is embedded in a early type galaxy, but with a disk, gas disk. And the jet, well, you see the dust lane here, and the jet kind of entered the disk. That if you want to see the effect of the jet is, of course, the perfect geometry, because as full, interact with the gas. So for this object, we knew a number of things. We knew that there were plenty of outflow in different phases of the gas, as I've shown you. This is a recurrent thing that we find. So this is actually in H1. The first thing we discovered, and was really a surprise. So this is the rotating disk, large-scale disk of the H1. And in the center, there was this huge, broad absorption that turned out to be against this Brighton lobe. Really, with velocity, covering velocity well outside the rotation of the galaxy. Then we did more work. Clive did some work on the warm molecular and the ionized gas, all very messy and outflow. So the next step was to do ALMA, to really see what was going on in this object at the resolution, spatial resolution that we needed to look at this. So these are the first ALMA results. This is the disk now of CO. That is essentially the inner part of the H1 disk is all very similar. In the center, so this is CO 221, and in the center we found this very bright part of CO that is nicely coincident with the radio continuum. You see, it really follow nicely the radio continuum. But the thing that really tells you what the jet is doing is when you look at the kinematic. So this is a position velocity plot of this CO observation taken along the radio axis. So you see the radio scale up here. And the white curve is the rotation curve that you would have expected if this all the gas was just rotating like it does on large scale. This is what you would have expected. And the orange stuff is what we found. So you see immediately that there is a lot of gas that deviating from the expected regular rotation, and in particular on the location of this radio lobe, you have the broadest component of molecular gas. So we are talking about few hundred, many hundred, up to 700 kilometers per second deviation. So so this already told us, and this happens only at the location of the radio. After this, outside this, all goes back to very regular. So this is telling you that even a radio jet of potentially a radio-quiet object can do this, can disturb the kinematic of the molecular gas in these ways. So can do the job. So here is a summary of some other ALMA observation we took, because then we started to have taste the fun of this. So there are more transition here. And what we found was that not only the kinematic actually is disturbed by the jet, but also the physical conditions are changed. In particular, if you look here, the green part is the disk, so the quiescent gas, where the CO 322 to 120 is essentially the same as in any spiral galaxy that you would study in this resolution, while at the location of the jet, the ratio is much higher. So we interpret this as a gas that has higher kinetic temperature and also high density, by the way, and possibly, and actually has to be optically thin. So the physical condition of the gas are also modified by this interaction. That's quite interesting. So that's nice, but actually the gas that leave the galaxy is really a small fraction. So the mass outflow rate is not very high. It's 10 solar masses per year. You will see more numbers later on. But the gas that really leaves the galaxy is a small fraction. So despite all this work that the jet does on the gas, the actual effect is more on a kind of fountain. So the gas goes off and then will fall back in. So disturb the kinematic. That still may also prevent star formation, but it's a different effect that we want, what you would have expected if you remember the simulation at the beginning. Just to finish off with this gas, with this object, what we did was to compare with the simulation. So I told you that I expect a jet entering the gas and creating this bubble, let's say, of shocked medium. So this is up there would be the view from face on, if I could see this galaxy face on. What the simulation tells me that should happen. And these are actually comparison of position velocity, as you saw before in the previous slide, compared to the one extracted from the simulation. For a galaxy really where we put all the parameter of this disk, so the rotation and all this, well, we put the theorists. But we force them to actually extract the position velocity, and here you can see how this disturbed part is clearly seen for a situation of this type. So essentially, all this bit and pieces, I know is for one object, and you say, oh, one object. But actually, it's a detailed study that tells us that what the simulation are predicting for the impact of the jet actually can be seen. Okay, and by the way, if you have a cold gas, molecular gas in your outflow, and as likely being destroyed by the interaction, but then must reform in molecular phase, so must cool very quickly. And from the simulation, you can actually see which are the region where the gas can cool very quickly inside on shorter time than the dynamical time, and are this red part where indeed the outflow are seen. So it's kind of coming together to a first order. So this is the first take-home message that I have, that even for a low luminosity, a low power jet, you can see the effect in this way. Of course, this was the best situation we could find, the jet entering the disk. But still, there must be also, all the phases of the gas are present, and there must be also efficient cooling to produce all these phases of the gas. But the final effect seems to be more of the type of galactic fountain. So let me move on to more the statistic. Okay, this was one object, so if we could do some statistic, would we find more of them, or what would be the fraction? So we have done this with the H1 because that was the faster thing we could do, the easier. We did a sample of 250 objects selected from Sloan and First, so we could quickly observe them using Vestabox. So we did this a few years back. The molecular gas, I don't have such a large sample, but one day will come. Actually, will come very soon. Clive, yeah. So, of course, takes longer to detect, to observe with ALMA. But I want to show you at least the result that we have for the H1 absorption, because H1 and molecular gas, they go really together, as we see in many of the objects that we have studied. So, okay, so we did the H1 in H1 absorption. There is no way at the moment to detect outflow in H1 emission. That's a pity, but the sensitivity is just not there. So absorption is nice because it only depends on the strength of the continuum that you have behind. So if you have a reasonably strong radio source, you can go to very low optical depth, and so detect also small amount of H1. So that's good, and you can do actually quite quickly. So even better. So, and what we of course has a limitation. The absorption, you know where the gas is only in front of your continuum, so you have a partial view of your object. Nobody's perfect, so we had to be happy with that. So what you see typically in absorption is something that people have done since ages. Very often radio galaxy have H1 absorption. This was well known, and typically is around the systemic velocity of your galaxy. So typically is associated with the circumnuclear disk. Fine. It's good to know, but that's not exactly what we want for the study of the feedback. But there are a number of objects, and I'll show you a few cases, but one is here, where in addition to the few hundred kilometers per second absorption at the systemic, you have a very broad blue shifted absorption, wing of absorption. When I say very broad, I mean up to 1,000 kilometers per second. Yep. Yep. The source of condition is my radio galaxy. Yeah, it's the AGN. Yeah. No, it's good to, I tend to give for granted few things. But the source of continuum is my core and my jet of my radio source. And in front of it, Of course, not in every case the gas is in front, but if in front of it there is gas, I see an absorption and I can see this, but I can also see gas that is outflowing or infalling. But the blue shifted tells me that it's outflowing. There is no doubt because it's in front, so it has to be outflowing, and I find this broad absorption up to 1,000 kilometers per second outflowing. This was already surprising in itself, but we got used to that. So, okay, so we did this survey where actually I should have put the continuum of this object, but I didn't. So these are only some of the H1 absorption that we found. In some cases are very narrow, are at the systemic velocity, that is this dashed line. In some other cases, they have clearly, typically a blue shifted wing. Almost never, actually, never the redshifted, equivalent redshifted wing of this amplitude. So we classify all this as outflow. This is a very shallow survey, so you should see there are also crappy data, but okay. So about, we got about 30% of detection in H1 and about 5%, between 5 and 10, show this, this broad wing. And it's a lower limit because you pick only the gas that is front of it. So we did this, and the most interesting, the thing that I want to point out here is that most of the galaxies, actually the majority, the great majority of the galaxies that have this broad wing, blue shifted, are either young or restarted radio sources. And I can talk for hours about how you classify young radio source, but maybe we should do at the coffee afterwards. But we have, from the spectral property, the possibility to say this. And so this means that, like you saw in the little simulation, the first part of the jet, when the jet starts, that's the crucial one, where most of this outflow of H1 absorption happens. Or when the source restarted in a second life or whatever. So this is an example that was also before. This is a radio source that in the middle has these two lobes. And against these two lobes, we see this integrated profile. And then if you have the chance to do higher spatial resolution, for example, with the VLA in this case, this is a position velocity plot that tells you that some of the gas is just at the systemic, that is around here, at this should be low, but okay. But some of the gas is very, very broad, is in this case almost 1,000 kilometers per second broad, and these are the location of this lobe. So we have a number of them, and we could derive a few parameters that you see summarized here. We get mass outflow rate in H1, about up to 50 solar masses per year. We can derive the kinetic power, especially for the one that we resolve and we have, and we can locate the outflow. We can also compare with the Eddington luminosity, and typical they are still only a small fraction of the Eddington luminosity. This is not what the simulation tell us that should happen in the AGN feedback, but this is what we find. And these are actually quite massive outflow, because if you look at the ionized gas of this object, the mass outflow rate is typically much, much lower. So, okay, so let me tell you, just give you the wrap up of this part. So we find this H1 outflow in young and restarted radio galaxies, so very similar to what predicted by the simulation. When the location of the outflow is known, they are against the lobes or already starting very close to the nucleus, actually. We did a lot of follow-up in VLBI that I have to skip for time reason, but we derived that the outflow in H1 started already quite close to the nucleus. That is also a surprise. I should be already there. And then as the source evolves, so for sources that are slightly larger, in addition to clouds of H1, we also find diffuse H1. So let's say the structure of the outflow also changed as the radio source evolve. That is interesting because it's, again, similar to the simulation. Slowly you destroy a bit the clouds that were there at the origin, and you have a diffuse gas. So this is what we are finding in H1 absorption using integrated spectra and VLBI cases like this one. And if you are interested, please ask me later. I can talk again for hours and hours. Okay, so so now I would like to show you. I would like to focus a little bit on the difference in radio power. So whether the difference in radio powers also tells you something or reflecting the impact of the jet. And so the object that I want to show you is one object where we thought this is going to be the prototype feedback in action that we can have, and where there is a young radio jet. That is this one. You see just a few hundred parsec. There is a merger still ongoing. These are some HST and VLT optical image. There is a quasar, so has also a lot of radiation, but is highly obscure, so must be in the phase in which the activity started not so long ago, is in the phase of clearing the gas around the AGN. That is exactly what feedback tells you should happen. So after I've convinced you, I'm sure, that the radio can do some of this damage, this we thought was the perfect case where we should see then the effect also on the molecular gas. So get away from the absorption that only tells us part of the story. Let's see the full Monty. So this object has been studied by Clive and Joanna all many, many years, and we, surprisingly enough, the outflow of ionized gas turned out to be very small. It's there, it's very fast, it's wonderful, but the mass outflow rate is very limited, so it cannot be what the feedback would expect, would predict. So there is also some fast outflow in the very center, in X-ray. One is called UFO, so all is there, but not the amplitude that you would have expected. So the question was, okay, maybe it's all in the molecular gas. We have seen that molecular gas takes part of all this feedback business. So let's look at it. So we did this with ALMA. And so, of course, everything that we had in mind as scenario turned out to be wrong. Well, yeah, not wrong, but different, as always the case. So in molecular gas, we actually found, we observed in two transitions at very high spatial resolution because we really wanted to see how the molecular gas was reacting to this jet and to this AGN. And what we find is summarized here. We find essentially three components of the molecular gas. The one associated with the merger, as expected. So this is a tail of few kiloparsec, and here you see the mass, molecular mass associated with that. We find, interesting, a small disk of molecular gas in the center, meaning that this gas that is accreted already form a circumnuclear disk around the AGN. So that's cool, because it's, despite the fact that this is young and all this has a lot of activity of the AGN, this disk can form. And we find a very fast outflow, but so you see the amplitude. This is again a position velocity. Also this one, I really like the position velocity. I think I even convinced Clive that this is the way to look at the data. So a very fast outflow, but all confined in a couple of hundred parsec in the center. So this is a large molecular outflow. This is our record order in this case, but only concentrated on the very central region. That was a surprise because we expected that there would have been a larger cocoon expanding and really yeah, showing the outflow in action. So this is again what we found in this object. This is the disk, the nuclear disk that I was telling you about. We even have the amplitude and the rotation. The jet is embedded in part of it, but part of the jet is already outside, and actually we think this part is a kind of remnant of jet, has a very steep spectral index that indicate that could be even a leftover, not fuel anymore. So a major interaction must have happened in the central region. And actually we see this effect of interaction again in the ratio between two transitions of the CO. Again, the gas that is falling in quite regularly, smooth, has the same line ratio that you would expect from quiescent gas, while in the very center, the ratio is opposite. So like in the first object that I showed you at the beginning. So again, the AGN, or the emission of the AGN, must affect the physics of the jet, of the molecular gas around it. So the conclusion for this object is, first of all, this is a much powerful radio jet. It's also a radio jet that kind of get out of the disk in a perpendicular, almost perpendicular way. So we are in a different situation compared to the previous one. In a case more like this, this is the jet, this is your disk. So the simulation will tell you that, okay, the jet escape much easier, but it would produce again a bubble that would diffuse in the disk. So we would expect that in this disk of gas, the conditions are indeed changed by this shock, cocoon shocks. And this could be the effect that we are seeing in the very center. So again, this has confused us anyway, because we find the outflow that we were expecting, but it's very limited to the central region. So again, where is really our feedback effect? I remind you that, okay, the jet, you can say, well, you took the wrong object, why you care about the jet? Forget about the jet. But this is a quasar, so there is also a lot of radiation, and the two effects can go together. Actually, they can sum up. So I would have expected even more. So this is the so this is telling us that the picture that we have also for this feedback effect is much more complicated than we expected. And so so these are the results from this object. Actually, this is not the only object where these kind of things are seen. It is obvious that the jet, the orientation between the jet and the gas around has an impact on what you see as effect on the kinematic, on the condition. This is a case, a nice cartoon that I thought was very nice, so I could not make a cartoon so nice, so I just stolen from the paper of Husemann on 3C273 that has, of course, a nice jet, where you can see how the cocoon, also in these cases of the around the jet, is used to explain the kinematic of the gas around. So it's not at the end of the jet where all the action happens, but it's more around the jet in expanding. So the jet orientation and the radio power, this, like the one I show you, are powerful sources, play a role. So we are getting into, and this is one of my points, in a very complicated parameter space that we need to explore and to build up the statistic about. So I have one last object that I would like to show you, because this, so far I've been focusing on the word outflow, but maybe outflow is a kind of more general thing. So one should consider also just the turbulence that this energy release impact and introduce in the gas around, and that's also an important parameter. So, and to do this, I reiterate that it's important to look also at low power jets, and so I would like to show you one final object that is part of this this group of objects that is growing very rapidly, because when you look at low luminosity AGN and you run out of radiation, your only hope is that there is a little jet there. So this is how they've been used, and this group of objects has actually increased as we proceed. So let me show you this object to finish off. This is a radio galaxy, a restarted radio galaxy. This is, as in the center, a little double source, that is this one, about a kiloparsec in size, and around very huge lobes of radiation, very low surface brightness radiation, very extended. And we think that this is the leftover from the previous activity of this object, and this is the new activity, relatively new activity. This object has also a lot of H1. This is a disk more or less on the same scale of H1, very, very regularly rotating. It's a beautiful disk. We know all about this, the rotation curve, everything. But if you go into the center, you can study the H1 in absorption in the inner kiloparsec. That, as I told you, in this case, I cannot do in emission. In emission, I have a much larger beam. But with the absorption, I can go in the center and look what the gas does in the inner kiloparsec using the absorption. And this is some of the absorption profiles that actually are far too broad compared to what I would expect if this disk here was just the one that would produce my absorption in the center. So in the center, there is something extra in addition to the regularly rotating gas. And we think that this is the effect of the turbulence produced by this jet entering this disk and messing up the kinematic of the gas. Again, with this bubble that I mentioned a few times and I've shown you from the simulation. And by the way, this object is also observed in CO with the RAM, so a single dish that has a very large beam. So, of course, we asked for time to do the higher resolution, and of course we didn't get, but okay. Interesting enough, if that CO would be regularly rotating like the H1 on relatively large scale, filling the beam, we would have a double horn profile of the CO that we don't see. The CO has a very, very similar profile. I flipped the emission of the CO to absorption just to compare with the H1 absorption. A very similar profile as the H1, meaning in our interpretation that must be in the same region, affecting the same way by the jet propagating into this. So essentially we attributed this higher dispersion that we find both in the H1 and in the CO in the very center to increase turbulence due to the effect of the jet. So one of the reasons why I'm showing you this is also, so this could be the geometry of this, if you would see edge on or face on, as the simulation would reproduce this object. This is the jet, this is the disk, and the jet propagating in the disk. And this is how you would see if you turn around. Fine. So this object is a liner, so it doesn't have much radiation to do this, to drive this increased turbulence. So we really think must be the jet doing this. But one of the reasons why I'm showing you is that something that we would like actually to do for more objects. This object has been observed by Khalifa, is in the Khalifa paper with all the information that you want there. Wonderful. So, and is a liner, but they have traced the line throughout the disk. So this is essentially part of the H1 disk that I showed you before. And this is the H alpha flux. But what they say is that in this region that you here see in orange, that's the part where the liners cannot be explained only by post-IGB stars or whatever. There have to be shocks in there to explain the properties of the ionized gas. So we think that this could actually be our famous cocoon that the jet produce, and in the inner part increase the turbulence and the sigma of the cold gas, but then keep on going. And how much keep on going, that's an important question, because we want to stop star formation, or at least quench star formation, or all this stuff. So how much this cocoon actually affected the gas is important, and maybe this is the answer to our question. This is from this integral field how we can see which gas is affected by this jet cocoon. So there are a number of objects, as I mentioned, where that are low luminosity AGN or liners, if you want, where there must be a low power jet doing the kinematic, affecting the kinematic of the gas and producing equatorial outflow, if you want to call. So outflow that are perpendicular to the jet because of all this situation that I just explained you and what the simulation tell us. So there is really a growing number, and as I mentioned, these are the ones where the jet will stay stuck in the medium for longer. So they really could dump a lot of energy in it. Okay, so let me just summarize all this number of things that I told you about the jet, but the conclusion essentially is that we find cases, evidence, where the jet can really couple very nicely with the medium, especially if it is a clumpy medium, and we find evidence of clumpy medium from, especially from the VLBI observation that I didn't show you, but trust me. So that we find also some a number of observational facts that are very in agreement, very much in agreement with the simulation that they are starting to developing and becoming more and more sophisticated. The impact seems to be stronger in young radio sources. That also makes sense. How it will evolve is something that we try to pin down as we observe more. I give you some of the number of mass outflow rate and energetic that are not quite up to the requirement of the big cosmological simulation, but that's just what we find. So maybe the theorist should change the requirement, but okay. And I show you how this jet can produce like expanding bubble or shock gas that could affect the surrounding medium, not only at the end of the jet, but really around the jet in an equatorial way, if you want to call, or perpendicular to the jet. And the impact is also on the physical condition of the gas. So that's also something to take into account. But what we find, and it's something that also the people studying the ionized gas found actually, is in most of the case most of the gas doesn't leave the galaxy. It rains back. So it's more a kind of fountain, the final effect of all this. And I mentioned at the end the possibility that this is done more than from outflow, but from increasing the turbulence of the gas. And so I just leave you with some general conclusion for you to, in particular, well, my attempt to show you that the jet can do something doesn't mean that they have to replace radiation or wind. I think we can consider all together this effect, this phenomena. Please don't ignore the radio quiet object. So just go and look what do they mean with the radio quiet, because sometimes they still have jet and emission. And so, but there are still some difference between what we observe, and not only in the jet feedback, but also in the ionized gas feedback. There is a discrepancy between what we actually find and what the simulation, the big cosmological simulation would predict. So I think a lot of improvement in both sides is necessary to really pin down this feedback, AGN feedback business. Thank you.
Okay, thank you. So we continue with the questions.
Sure.
And there are several here.
First, a comment. I like the realism or the honesty of your results. It's clear you're an observationalist.
Yeah. I definitely am.
Secondly,
yeah.
about the 600 solar mass per year result. That's a hell of an outflow. What's the idea? Either it can't last very long, or it has to be fed from the side. What's your take on that?
So actually, no, you are right. I've been always very skeptical about this large mass outflow rate. So there are a number of uncertainty, of course, in this number, because we don't really resolve the location of, so is all the outflow that is also, as you see, uncertain, but is all in one beam. So there are uncertain, but whatever you do remain large. So I would not bet my salary on the 600 solar mass, but it remains large. But you should also consider we are, indeed we mentioned that there must be, depletion time must be short, so meaning that this will disappear. So the idea is that will not stay. It's true that in this system we think there is still infalling of gas from the merger. So this depletion time maybe is a lower limit, but still after a while will be gone. I agree with you. But so there is some infalling from the merger that clearly is happening, partly going to the disk and partly being get rid of from the outflow, but will not last forever. Absolutely, yeah.
Okay, let's continue.
So, first of all, thank you very much for very nice review. It was very nice.
Thank you.
So my background is accreting black holes in X-ray binaries. I actually work in outflows as well, so I have a couple of comments and a question. So I really like your conclusion about the liners, suggesting that, and actually I wanted to add that the liners, we think that we have an equivalent in stellar mass black holes, which are black holes accreting at a low rate, in which we call the hard state. And actually that hard state, the main property of the hard state that we have a steady jet that you cannot resolve and is there all the time. And actually the kinetic luminosity of the jet sometimes dominates over radiation. So that goes very well with your conclusions.
No? Yep.
And on the other hand, I wanted to talk about the absorption that you see in H1.
In the last object?
Well, in
every object? Or?
No, when you have the absorption and then the blue shift.
Yeah, okay.
Because it's just a curiosity. Yes.
Like this one?
Yes. I'm not familiar with this transition, but which is the mechanism to produce the absorption there? So my question is that if there is absorption because you have a cloud that is scattering light out of your line of sight?
No. It's just neutral hydrogen.
So pure absorption?
Yeah,
okay.
Pure absorption.
So
this is just absorption. The uncertainty when I derive the parameter is on the spin temperature of so how the level are populated.
Yeah.
So there is a component also here of uncertainty in some of this mass, but because this is gas that we assume is close to the nucleus or anyway is affected by some shock, should be not the usual 100 or the low spin temp, but should be, usually we take 1000, but could be 800, I don't know.
Okay,
Very little is known.
So it's not a scattering, because otherwise you should see an emission component also.
No.
And just one final comment. When you mention radiation power outflows. Probably you are meaning those that are produced when you reach the Eddington luminosity, so by Thomson scattering. But also you can have radiation power outflow at much lower luminosities, thermal wind, line-driven wind.
Yeah, no, there are, so there are, for this, do I have anything? I don't know. No, I don't have really, no, I don't have a figure, but there are outflow really in the central part. These are really, this is an accretion disk, so are just outflow really wind, really close to the accretion disk due to the pressure from the accretion.
So radiation pressure.
Yeah. But then they move on, and then they shock the gas around. That's one possible scenario. Then there is also dust, so you can think of shock that, but also radiation pressure on dust and gas.
Yeah.
So
Okay.
there are different possibility as you move away from your.
Okay.
AGN.
I understand. My point is that to launch that initial wind, you don't need to reach the Eddington limit. You can do it well below the Eddington limit.
Yeah. But so there is an entire literature about
Okay.
that. There are other 10 talks.
Yes,
if
yes,
you want
sure.
to invite somebody.
Sure.
Yeah.
Sure.
Yeah.
Thank you.
Hi, Raffaella. Thanks for the very nice talk. So, these bubbles, do they have an impact on the properties of the stars around them? Or
Yeah, well, I was. This is why I mentioned the last object, because I was hoping you would tell me actually. So we don't know. Well, we don't know. Do we know? No, we don't know, because we are really looking at small scale, kiloparsec. Let's say all the one that I show you are the outflow where I found something are let's say at most a few kiloparsec, at most. And for those objects, we have some optical data, but not much. And typically, we don't look at the star. We don't like stars. We look at the gas.
no, I just wonder, because you have all
but
for
yeah,
that Khalifa galaxy, you have all the information you want.
But yeah, exactly. For this one, maybe I should look back. I cannot tell you. You should tell me. So there are plenty of plots, of course, describing all this. And what I got struck about is that the properties of the equivalent width of the gas was changing, and this is what these two parts reflect. I only look at that, but it would be very nice to know more about the stars. So what should I look into? Well, maybe later.
I wonder
we
whether
can-
metallicity it will be
yeah.
impacted in
Ooh,
some way.
metallicity.
I wonder whether kinematically there will be some non-radial motions kicking in. I don't know. Probably not, but
I don't think. Maybe something specific. I mean, maybe once you have a candidate, something also more detailed should be done. Some observation really because this would be really good to know. If I'm right, and then there is something moving in this way, do I see on something apart from the gas? I don't think we have any. Yeah, but. Exactly. Yeah. Yeah.
Well,
Yeah.
I might say, I was going to ask something different, but I might say in some cases we have studied the impact of this ionized gas being driven by jets. When it gets circularized in the galaxy, you see a ring of star formation. So indeed, it rains back and you form a ring.
A ring of star
A ring of
formation.
star formation. You have many inliners. you
Yeah,
see that.
yeah, true. But I thought it was due to something completely different, some resonance.
Well,
or
you
some-
are putting out material, it's getting
Yeah.
out, it loses momentum, it gets circularized, and you form a ring.
Okay.
In some cases, we have seen that. I mean, maybe you have a dye, you don't see it, you have to look in infrared, high angular, etc., etc.
So in a way, this is a really ideal case because of this. Because we have the H1 emission, so we can say everything that deviates from that must be funny, gas affected. So this is how it's easier to compare the absorption with the emission. So it's a really powerful way we don't have for every. So, okay, but
So, yeah, my comment was that perhaps we had to get a little bit relaxed with the predictions from simulations. You know, I think it's quite overwhelming now that the AEN is not making much the job as they needed in the simulations, particularly because many of these jet mode or radio mode is happening in low Eddington sources, as you might see, when they become very efficient, or when the most of the kinetic energy you are measuring, comparable to the radiative one, is in low Eddington sources. So,
yeah, not all, because like this one, yeah, this one is a quasar. I don't know.
yeah, I think
So it's a kind of mix, and I think this separation between these two modes of feedback, I think is too black and white.
I think
This is the
yes,
conclusion of
because there must be a transition.
Yeah,
There
yeah.
must be a transition. But I think that in quasar mode, probably where you are dominated is by the radiative luminosity rather than by the kinetic. While when you go to low Eddington, you are much more dominated by the kinetic energy. So, and then I have just a very short question. I was a bit of what John was saying. You have these very high flow rates. I was in H1, I think it's quite obvious when you see this evidence for outflow because you have the absorption. But in all other cases, it's so evident, it's so compelling that you have outflow and non inflow because you have out, you have to put in. I mean, we cannot get all the time looking for out, and we are not putting material in. So it's so compelling.
that
I
we
always
have
question the
outflow.
outflow from other traces.
Also, typically the outflow actually is interesting because at least in many cases, what we derive from the H1 is very similar to what we derive from the molecular gas. So the two phases seems to go together. So in H1 I see an absorption, so I know it's in front, I know the geometry, and somehow I get something very similar also from the molecular gas. Don't have many objects because the telescope are spread a bit in an annoying way. ALMA is in the south, the good radio are in the north, but okay, will change. So, but they seem to go really together. So I was, and the accretion typically happens at lower velocity, certainly for the H1. So the extreme velocity seems to be always associated with something that looks like an outflow. In the first object, they are not even extreme, but they are all throughout the radio, and they are perfectly reproduced by the simulation of. So I would find very strange if there is inflowing gas only where the radio source is. So I know what you mean. I know what you mean. It's not always so obvious, say, outflow, but in many objects I would almost bet my salary. That's not true, but okay.
I think it's my question, now my turn. You've mentioned these high outflow rates, not even even discarding these 600 solar masses per year, you're talking about 10 or 15, and if I understood you correctly, you say that they never make it very far from the disk. And my question is, how do you know? Do you have the sensitivity to really detect 100 kilometers away from a galaxy?
No, so I know from not the mass outflow rate. So the mass outflow rate, no, let me go to this object, maybe it's the easiest one. So what I know is that I know from the velocity. I just use the velocity. So in this case, the only velocity, if I measure, if I derive an escape velocity, the only gas that would have velocity higher than that is the one at the extreme of this distribution. You know what I mean?
But the escape velocity could be 100 kilometers per second or so. I mean, escape velocities are not very high, really.
Well, in this, these are a few hundred, but these are also few hundred kilometers per second.
What I'm saying is that, I mean, as soon as you have a few, 100 kilometers per second or so.
No,
it's fast enough.
so in this object, the escaping velocity is always in the object that I'm looking at. They tend to be a few hundred, at least 400 kilometers per second, if I remember correctly. So only the gas that goes above that, with velocity above that, is really escaping. This is a very rough. I realize that. And so it's not what I mean. Is not all what I call outflow is a super high velocity and will all be gone. I'm only doing a rough calculation based on the velocity of the gas. And
No, I understood the argument, but
you think is no good?
well, and you can even have some pressure gradient that is like driving the
okay,
outflow.
okay.
So
Then
this argument is
No, so
I
this
understood
this is
I
a
now
very
understand
rough,
the argument. But
very rough. Just taking everything, not even considering the geometry, just taking an average.
But you don't have observational arguments in addition to this one, like non-detecting gas far from the galaxy, to say that the outflows are not maintained all the way
I'm
up
just
to.
I'm just doing a reasoning based on the velocity of the gas and how much of the gas goes at high velocity, the distribution of the velocity of the gas, how much of the gas goes really at higher velocity, let's say above 500 kilometers per second. And that's only a fraction of the gas that is in this disturbed gas. And so it looks like only that part may really be gone, the other would go up and down a bit.
Okay, one last and short, I hope, question with answer, because we are behind. We have afterwards a scientific coffee, and there are already people waiting, so we should finish this. Yeah.
Very short, I will be short. So Raffaella, very, very nice. And now that you have studied so many sources in different gas phases, is there an evolution of the outflow in gas phase? You know what I mean?
Yeah, well...
do you think that there may be an evolution?
You mean that the molecular or the H1 is in the inner, and then there is the in the location, or in time scale? No, I cannot tell you that. No. So we are trying to see, for example, in this case. Well, I didn't put the slide, but the ionized gas seems to be more extended. The outflowing ionized gas seems to be more extended than the molecular and the H1. So there could be that you have molecular and H1 only in the inner part, and then outside becomes all ionized in outflow or whatever. But in time, the only thing I know is about more the structure of the outflow. I need more ALMA time.
Okay, thank you. Let's
Thank you.
congratulate. Okay, and then scientific coffee has already said is already going on.
Oh. Okay, what should I do?